Hi guys, and welcome to this video where we're looking at position vectors. So this feeds nicely from the video before where we were looking at column vectors, so the numerical way of describing vectors. This video, as it says position vectors, we're thinking about how we can use our vectors to move from one place to another and think of them in combination with other vectors. So the very first thing I want to talk about is if I just have any random vector which I've drawn here, I've put no thought into it about the distance or the direction it's going in. I just drew a straight line on a few moments ago. So I'm just going to call that vector A. It takes me from this point up to this point. Now if I wanted to go, instead of from here to here, here to here, what could I do? Just have a think how I could actually reverse that movement. Well, I could actually just change the direction of my vector. So instead of moving this distance to the right and this distance up, I can think about moving a distance to the left and down. So I would just be going exactly the same distance but in the opposite direction. So I can just change my sign. So that is a fact about vectors. You can change the direction they're going in simply by changing the sign. It doesn't change the length, it doesn't change the gradient of the vectors, how steep they're going. It just changes whether they're going from here to here or here to here. So what I've done is just written out two vectors pretty much at random actually, which are going to be quite a nice demonstration. So I always like to think of position vectors as describing a path that I can walk down, but I can only walk down paths that kind of link to these vectors. So I just want you to imagine I can only walk 4 to the right and 3 up, or 2 to the left and 1 up, and in some combination of those. So they're separate movements, but I'm going to put them all together to get from one place to another. So let's just imagine I'm starting here. I'll call that point X, and I want to walk, I want to apply vector B. Just notice I didn't underline that, sorry. So I'm going to walk 1, 2, 3, 4 to the right and 1, 2, 3 up. So I'm going to do a little dot there and join those up. So far I've got a visual representation of vector B. It takes me from here to here, 4 to the right and 3 up. Then I could apply vector C. I've got to this point and I want to walk 2 to the left and 1 up. So I'll count that out. 1, 2 to the left, 1 up. And I'll mark that on. And add my little arrow as well to make it really clear what direction I'm going in. So that was vector C. Now I could apply vector C again if I wanted to. I could go 1, 2 to the left and 1 up. And again, call that vector C. I want to walk vector B now. I want to go 1, 2, 3, 4 to the right, 1, 2, 3. Just to be clear guys, I'm making this up. You'll see why I'm doing this in a moment. Okay, so this part of my journey is pointing in exactly the same direction. It's parallel to my other vector B, and it's exactly the same length. Okay, I again walked 4 to the right and 3 up. Okay, I would like to apply vector C, but this time instead of going to the left and up, I'd quite like to go to the right and down. So I'm going to apply vector negative C. So 1, 2 to the right and 1 down. So let's just join those up. I'm going to mark that in. That's vector negative C. Okay, you'll see that they are parallel to vector C. And now I'm going to apply vector B again. So I'm going to go 1, 2, 3, 4 to the right and 1, 2, 3 up. And I'm just going to mark it on there. And I'm going to call my endpoint Y. So what I'm going to do, and what a question might ask, obviously you wouldn't have to do all that yourself, that would already have been done for you, that path that's been drawn out. You might want to find the vector taking you from x to y. So that is what that notation means. You're going from x to y. So what you've actually done is you've started off by walking vector b, and then you've added on another vector. You've added on another part of your journey. You've added on vector c, and then you added on vector c again. Then you added on vector b again. So I'm just tracing my steps here. B, and then C, and then C, and then B. Now when you got to here, you didn't add on vector C, you took vector C away. And then when you got to here, you added on B again. So just like algebra, when we collect like terms, we can tidy that up a little bit. I can add up all the B's I did, so work out how many B's I moved in total. So 1, 2, 3. And then work out how many C's I moved in total. So C plus C is 2C. When I take C away, I only move 1C in effect. And if you think about it, that does make sense. This movement here cancels out this movement here. Okay, I could have simply moved 1C from here to here and then applied vector B, and I've ended up here. I've just added in two movements here that cancel each other out. So the vector from x to y, in terms of being C, is 3b plus c. And there's a nice physical link here. Now you probably won't be able to do this in an exam. It was likely going to be on plain paper. But the fact it's on squared paper means I can really show you the link between what we've got here and our basic idea of vectors, as how far to the right and how far up and down we move. So 3b plus c, I know the values of b and c, so I could actually work this out. This is quite a nice practice for my calculations with vectors. So I've got 3 lots of 4, 3, that's my vector b, and then I'm taking away 1 lot of minus 2, 1. So 3 times 4 is 12, 3 times 3 is 9, and then I'm taking away, I'm taking away minus 2, 1. So if I calculate that, sorry guys, I've just completely misread that. I'm adding on C, so there should be a plus sign in there. I thought my numbers didn't seem quite right. So I'm adding on minus 2, 1. So 12 plus minus 2 is 10. 9 plus 1 is also 10. So what I've just said here is that to move from x to y, I would have to move 10 squares to the right and 10 squares up. Let's just see if that's true. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is. Okay, so this version here of getting from x to y is just kind of simplifying it a little bit. Okay, so using and applying the vectors I already know and thinking, well, what is the most simple route to get there using just those vectors. Okay, and it should actually have the same effect as moving that far right and that far up, and we can see that it does. Okay, what I'm going to do then, I have seen this question, I really like it in a textbook. I'm just going to go through it with you as it is a bit of an introduction into some of the questions that could be asked in an exam. So this question says that wxyz is a square and m is the midpoint of that square. And we've been given 2 vectors which we've called a and b. So vector a moves you, well, it's described here as moving you from z up to w, so it moves vertically, the height of the square, and vector b moves you from Z to Y. So it moves you the width of the square and it moves horizontally. So both of those vectors are actually going to have the same size, but they're going to be pointing in different directions. One goes up, one goes to the right. So we're being asked to find the vector that would take you from W to X. So what movement would take you from W to X? So you are going to be wanting to move the width of the square. And what other vectors have we seen which move as the width of the square? Well, this one down here does. Okay, I'd have to move in exactly the same direction and exactly the same distance to get from Z to Y as I would to get from W to X. Okay, so the vector which takes me from W to X is simply going to be vector B. That movement will take me from W to X. Now what about the movement that will take me from W to Z? So I know that Z to W will be given to me straight away by A. Now what if I wanted to go from W to Z? Well, we've seen we can just apply a minus sign to our vector to reverse the direction. Okay, now we need to think here, how do we get from Z to X? So it would be really nice if we had some other vector which took us straight there, we could apply it, but unfortunately we don't. So we need to use a combination of these two vectors I've got here. So I'm just going to imagine tracing a path from Z to X. So it's going to have to be an alternative path. So I could go from Z to Y, and then from Y to X. So moving from Z to X is exactly the same as that. I'm just going to write that down actually. So it's the same as going from Z to Y, and then adding on the vector from Y to X. Now Z to Y, I've already seen, is vector B. It says so here. And what movement would take me from Y to X? Well, we can see it's parallel and it's exactly the same direction as this vector taking me from Z to W. It's the same movement. So I could add on A. So vector B plus vector A would take me from Z to X. Now I could actually apply those in any order. I'm just going to emphasize that by changing the order. I could apply vector A and then vector B. It doesn't matter, I'm still going to get there. So the order doesn't matter. Now Z to M. There's two ways I can think about this. The first way is to think about it in terms of the only two vectors that we were given. So it's the midpoint. So I know it's going to be halfway across the square, and it's also going to be halfway up the square. And I'm starting at Z. So if the vector A takes me from Z to W, half of vector A will take me halfway from Z to W. And if I know that vector B takes me from Z to Y, half of vector B will take me halfway from Z to Y. So if I applied that vector here, I'd get from here to here. That would move me from Z to M if I went half the distance of A and then half the distance of B. So I'm going to write that down. Half of A plus half of B. That would get me to the midpoint. Alternatively, I can think, well, Z to X is a diagonal. I've already worked out what that is. It's A plus B. And the midpoint is going to be halfway between Z and X. So it's simply going to be half of vector A plus B. It's half of ZX. So I'm just going to annotate that. I've just said here, I've just identified that this vector is half of ZX. Okay, now vector M to X. So how would I get from here up to here? Well, I've already seen to get from Z to M, I would go halfway across and halfway up. Half of B and half of A. Now I'd have to do the same thing again. Vector Z to M and vector M to X are exactly the same. Okay, so I'm just going to put those down again. Okay, now WM. To get from W to M, I would have to go half the distance to the right and half the distance down. In other words, I'd have to go half of B and then half of the opposite of A. So I'm going to write that down. I would go half the distance and direction of B, and then I would go the opposite direction to A and half of that distance. So minus half A. Okay, sorry, that was my cat sneezing in the background if you heard anything there. And then finally, I've got vector M to W. So I've already seen that W to M takes B would be achieved by doing half of B and taking away half of A. So it is going to be the negative of that vector. Negative 1/2 B minus 1/2 A. So you could actually leave your answer like that. I think that would be acceptable in an exam. Or you could multiply both of those by the negative. You could apply the negative to both of them. So it would end up being minus 1/2 B plus half A. Okay, so that is saying, just to double check that it works, it's saying that I have to go half the distance of A, so I'm starting at M and getting to W, so I go half the distance of A, and then I take away half of B, so I go like so. So, I'm under no illusions, vectors can be a topic that some people just can't get their head around. It can be really difficult, but hopefully these videos have helped a little bit. Make sure you watch the other two, and it will make a lot more sense. I'll see you later, guys. Thanks.